Okay, the major idea today is that moving charges are surrounded by a magnetic field, and these magnetic fields can interact with other magnetic fields to create a magnetic force. So we have two permanent magnets that are generating their own magnetic field. We have a particle moving to the right with a speed v, and as it moves, because it's charged, it will create its own magnetic field. The two magnetic fields interact and produce a force, and that force will be equal to the product of the charge times its speed times the magnetic field that it is entering. We can see this magnetic force on this electron beam that gets deflected by this permanent magnet that I bring nearby. To find the direction of the magnetic force, we use what's called the left-hand rule. And what we do is we point our fingers in the direction of the magnetic field. Since it's x's, that means the magnetic field is going away from us. Our particle is moving to the right, so our thumb points in the direction the particle moves. The force on this charge will be down. That's the direction of the palm. So your fingers point in the direction of the field, away from you. Thumb points in the direction the charge is moving. That's to the right. And your palm pushes in the direction of the force. That's down. So to look at how it would actually behave, we'll fire it into the magnetic field again in slow motion, and you can see the particle will deflect downward. Realize once it starts moving downward, the direction your thumb points changes, and therefore the direction of the force changes. So in reality, this particle would follow a circular arc, in this case a semicircle. So as the object moves, you keep rotating the direction of your thumb, and your palm will always point at a right angle to the direction of motion. That's the condition for circular motion. Okay, let's try this one. So our fingers now point to the right, the direction of the magnetic field. Our thumb points up. So this time the particle should move towards us. So as it's going up, it's going to start to move towards us, because that's the way that our palm is facing. Okay, this is a positive charge. When dealing with a positive charge, use your right hand. So this time the particle is going to move down toward the ground. So point your thumb toward the ground. Point the fingers of your right hand to the left, and this time your palm of your right hand moves away from you. So this particle, as it was moving through this magnetic field, would be moving away from us, in addition to its original downward motion. Okay, finally we have a particle with a dot. That means the particle is coming towards us. So point your thumb toward you, point your fingers to the right, and this time the particle would be pushed downward. Okay, the particles do not necessarily have to be on the loose. They could be in a wire. So if we have a pre-existing magnetic field, we have a wire carrying a current I, and if the length of the wire in the field is L, we get a formula for force magnetism of BIL. B is the strength of the field, the I is the current in the wire, and the L is the length of the wire that's actually in the magnetic field. Okay, to make sure you know what you're doing, see if you can figure out the direction of the forces on these 6 different examples. And see if you can work through this problem with your math equation. Use the first equation because the electron is on the loose. Okay, one of the places where these deflecting electrons by magnetic fields is important is in a TV picture tube. So if you can draw out the picture of this picture tube, the television picture tube uses an electron gun, firing electrons through a deflection coil, moving through a vacuum tube that eventually hits a phosphorescent screen. The electron gun is triple barreled. That's because it needs to fire electrons for each of the 3 primary colors. The coil will be an electromagnet that's going to deflect the electron to different points on the TV screen at different moments in time. The screen itself is covered with a phosphorescent material that will glow when the electron hits it. When we zoom in on the screen, we see that it's actually made up of tiny little pixels, and as we continue to zoom in, we see that they are the three primary colors of red, green, and blue. And you could see that the red is barely lit up for this region of the screen, so that means it will get a cyan color. If all three colors were lit up, you'd get a white color, and if none of the pixels are lit up, it would appear to be black. So you have your electron gun firing electrons from three barrels. One is going to hit the red, one's going to hit the green, and one's going to hit the blue. Realize that the electron is only hitting one spot on the screen at any given moment in time. The deflection coil deflects it to different areas of the screen at different moments, and it will actually trace back and forth across the screen to paint a picture on the television set. It will do this many times per second, and the illusion is that there is a static picture on the screen at any given moment. But realize the electron is only hitting one spot at any